So the purpose of this talk is really not to present a solution for the hard problem, obviously, which is the consciousness, right? However, not even to discuss the theories of consciousness, because there is a lot of that around. However, I'm going to limit my quest here to answering the simple question with a practical value in improving the resiliency, efficiency, and scalability of distributed applications. And so this is really looking for how we can infuse some of the cognitive features into the digital automata so we can mimic what conscious entities do so well, which is the business of sensing, modeling, analyzing, predicting, and taking action to maintain stability in the face of non-deterministic and rapid fluctuations while dealing with finite resources. So this is really the goal. And it turns out that there are some interesting new ways to look at this problem, and we can actually come to some kind of application of this. So here is basically what it is very likely on the basis of philosophy that error has to be caught, explained, and corrected. The complexity of the living organisms would not live for a millisecond. Such a system is so integrated that it operates across errors, and that is what we really want our computing systems to do. The second thing that is very, very important for this study for me, and also make some new things that we are proposing, is made it possible was, according to the general theory of information, information belongs to the ideal world of structures, which is the scientific incarnation of the world of Plato. Ideas are forms. This place of information looks contradictory to the assumption that information is physical and to the fact of the incessant presence of information in nature, society, and technology. And so Mark Bergen essentially says that information really doesn't have a physical form, but it is really being carried. And he has the whole general theory of information allows us to really address what is structure, what is mental structure, what is physical structure, and how do we represent the knowledge, and how do we take information, convert it into the knowledge. And therefore, we can actually look at how we can essentially bring some of the features like autopoiesis, which describes a technical system that is capable of regenerating, reproducing, and maintaining itself by production, transformation, and destruction of its components, and the network of processes in these components. This is a very important part because this is what allows us to, if we can infuse autopoiesis into digital automata, they become self-managing, and therefore they become auto-scalable, auto-failover, and self-protecting, and so on and so forth. So is that possible? That is one question. The second question, of course, is the cognition. On the other hand, is the ability to process information, apply knowledge, and change the circumstance. And obviously, there are a variety of models here that different levels and so on and so forth. So how can we model cognition and also infuse that into the digital automata? So the whole, real impetus for this comes from the general theory of information, which essentially says that the world of structures contains physical world, the mental world, and they are represented in the world of structures. And the world of structures allows us to essentially represent knowledge, transform information into knowledge, and so on and so forth. So if you look at really the mind, body, brain metaphor, the way it works, you sense, observe, and manage, then you remember, memorize, and you either mimic and learn, or you also abstract and model, and then you reason and predict, and then you have a free will, act or not act, and then you go back and you act and basically sense, observe, and so on and so forth. So this is really the sentience, resilience, and intelligence come from these kinds of.
Start with something very ludic and simple. Many of you probably have seen this before, but if you have not, this is an illusion. What's the illusion? Well, you see a checkerboard, it seems perfectly fine, until I draw your attention to the fact that at these locations, you have exactly the same luminance. It's the same exact gray level. But Of course, when you look at the whole checkerboard, it looks like there's one gray, dark gray and one light gray cell. So what's happening here? Well, if you look carefully now, you'll see there's a sort of shadow. Of course, it's just a dark part in your retina, but your brain treats it as a shadow, thinks that the light comes from the right side, which is compatible with this brightness here, and there's a cylinder that casts a shadow. And so what your brain is doing is removing that shadow before letting you see the scene in 3D. It's also thinking that these are squares, by the way, well, they're not square at all. The point here is that consciousness is the result of a long series of computations. What we are aware of is not the raw image, of course. What we are aware of is a subjective feeling, which results from computation. Another point also is that even a machine would probably experience the same illusion. If you wanted to design a machine that gets to the heart of things, what reality really is like, it should really recognize a checkerboard here and would therefore be submitted to the same illusion. First, I will tell you about some of the contents of this first book, Consciousness and the Brain, and new data to suggest that basically I think we begin to understand the basic operation of conscious access, how we perceive something in the external world. We have identified signatures of consciousness and we're progressing in this respect. They are shared between animals and human. And we are guided by a theory, the global neuronal workspace theory, and the data so far seem to converge rather nicely. But in the second part of my talk, if I have enough time, I would like to tell you a little bit about new ideas that I developed in the second book, How We Learn, and I developed this second idea that the contents of consciousness may be different in humans. They're richer in humans. We possess a language of thought, which leads us to unique competencies for language, for math, for music, conscious representation of ourselves and others. And we'll try to show you, therefore, that these are abilities that require specific models. In terms of AI, this is really a neuroscience talk, I think, but here is where AI is going to come in. First of all, it's used as a tool in order to decode brain signals and to classify patients with disorders of consciousness based on these signatures of consciousness. And second, it's used as a potential model. I think it's achievable to model the global neuronal workspace, and we've just heard from Josh Bengio about this. But I will also claim that the current AI remains limited in its ability to capture human behavior and propose some challenges that I think are not met, at least so.
So what else do we need to know about consciousness? So the important points here is that there are a large number of computations, and it is possible to infuse some of these learning processes.
We are not passive exhibitors of visual or auditory or tactile images. We have selves. We have a me that is automatically present in our minds right now. We own our minds, and we have a sense that it's every one of us that is experiencing this, not the person who is sitting next to you. So in order to have a conscious mind, you have a self within the conscious mind. So a conscious mind is a mind with a self-image. The self introduces a subjective perspective in the mind, and we are only fully conscious when self comes to mind. So what we need to know to even address this mystery is, number one, how minds are put together in the brain, and number two, how selves are constructed.
So this basically what we learned from all of the neuroscience studies is that computation is important, large number of computations at various levels, and they have to be all integrated with a common representation. And how minds are put together is really a representation. And then you need to have a self, and that self is the anchor with which it is representing all of the knowledge about itself and also its interactions with the external world. And in order to do that, essentially, I recommend Damasio's 16-minute presentation. It clearly explains how the neural maps and brain imaging and all of this stuff allows us to essentially identify how the representation of knowledge that comes from various stems from the medulla oblongata and takes all of that sensory information and passes it on to higher level, and the neocortex actually has an integrated view. And here is, for example, this red part is actually, if this part is not working, you really lose yourself. And then you won't be able to actually, sort of have consciousness. Whereas if this part is gone, you still have the self, but you may not be able to function. And so there is a very interesting, all kinds of information that is provided now so that we can sort of understand the business of managing life, how it is happening in the brain. And then we can identify what are the things that contribute to autopoiesis and what are the things that contribute to cognition, and how can we actually bring those features into the digital automata so that we can go beyond the Turing machine. So consciousness is the interaction between the body and the brain with a model of the self, which provides the stability and the interactions with the outside using 5 senses, the 4E cognition, basically embodied, embedded, extended, and inactive. And these 5 senses essentially provide all of this information. Interestingly, all the representations that come from whether it is oral or whether it is visual and so on, they become neural maps with a common representation. And that representation is essentially, if you read, for example, the 1,000 Brains from Jeff Hawkins, you will see how the cortical columns represent neural maps and how they are used by the cerebral cortex and the neocortex in order to process the reasoning and so on and so forth. So the important point here is really global knowledge networks, neurons wired together, fired together. Elevated cognition gives you the 6th sense, and all of the 5 senses are coming with the information. And here is where all the common representation happens. And that common representation then is used in order to address, cross-functional, all kinds of reasoning and so on and so forth here. And so the reference frames essentially in the biology seems like provides a common knowledge schema, and neurons fired together, wired together. And essentially here, when you bring it from memory, then you will see that essentially the neurons that are wired together, fired together to give you the images and maps and time series and so on and so forth. So he basically says that, this autobiographical self is the one which provides the thinking. So if you look at this, essentially what we are talking about is now a model where there is a symbolic computing with the DNA, and there is sub-symbolic computing with the neural networks, and there is the super symbolic computing with combining these two with a common knowledge representation. So that is the model that we want to bring to actually, this is basically some statement by Stanislas Dehaene saying that there is a need for a theory, just like when kinetic theory and statistical mechanics came, we understood how microscopic properties actually translated into macroscopic properties. So here is our path to digital consciousness. What we are suggesting is that there is in fact, we can actually take all of the knowledge and we can represent that in structures. And those structures are now basically the Turing machine, which is the equivalent of a digital gene, which essentially provides a symbolic computing. And the neural network is the digital neuron, which provides sub-symbolic computing. And this model is not enough. And therefore, we need to provide the super symbolic computing architecture overlay, which uses and repurposes the existing symbolic and sub-symbolic computing so that you don't have to forklift and change anything. Just like the evolution, your neocortex actually repurposed your cortical columns and essentially used everything that it has, and it didn't really reinvent anything, right? And so this is the model, and we come up with essentially identify what are the missing ingredients in this Turing computing-based model with the symbolic computing and super symbolic computing. One is the missing self, concept of self. So if you see, the key property of a general purpose computer is that they are general purpose. We can use them to deterministically model any physical system of which they are not themselves a part to an arbitrary degree of accuracy. So their logical limits arise when we try to get them to model a part of the world that includes themselves, right? And so that is what we are trying to fill here and come up with a new model where the self computer and the computed become a part of the model. And so it essentially allows us to go beyond the Church-Turing limitation. And also the Church-Turing limit thesis actually is limited by finite resources. And so how do you optimize your resources? And that's another issue. And so we essentially now proposing a super symbolic computing model where you have essentially a overlay of existing architectures where you have your regular cloud computing, where you can keep AWS, Google, or any cloud, and you can essentially use this overlay architecture to essentially create an autopoietic function node which knows how to use these resources. It uses the sensors and the actuators, and this becomes a distributed self. And therefore, the autopoietic network node and the cognitive network node, they provide overall global coordination and so on. So the autopoietic function provides all of the self-management properties, and the cognitive layer provides all of the cognitive functions of the neocortex-like functions, essentially, for example, reasoning and so on. So this gives us actually a location transparency. It becomes applications now become path agnostic or IaaS agnostic. That means I don't care what infrastructure I use as long as I know how to provide the services from them. And that is the function of this autopoietic function node. And we have a cognitive function node, which essentially then manages all of these applications as a distributed body. So essentially you have multiple instances. This could be running a AI function. This could be running a algorithm, and this could be running multimodal analysis and so on and so forth. So using this, we can now create actually a combined model with symbolic and super symbolic, sub-symbolic and super symbolic architecture, where you can actually now use deep learning as a providing the data for a data knowledge model. And that knowledge model is essentially based on all kinds of information that you have about the domain. And that gives us a representation in knowledge structures. And this is where we use essentially the Mark Bergen's general theory of information, which says how to use structural machines and how to use structures and how to create knowledge structures with not only entities, but relationships, but also the behaviors among them. And therefore, they'll behave like a knowledge network where functions and nodes and links essentially provide this global network of knowledge representation and also communication. And that's basically what the current model is. And using this now, you can actually now create this structural machine, which is essentially the super symbolic computing, which uses both of these and also uses reasoning module here, which essentially now uses all the information, including the history. So that this is a non-Markovian reasoning, not just Markovian based on current state and only the next state. And so this is essentially the idea that we are implementing right now to provide some self-managing applications across multiple clouds and so on and so forth. In addition, this also allows us to use cognitive multimodal deep learning, for example, right? So I have a cognitive, this is my hardware cognitive agent, essentially manages and gives me a deep learning AI stack. And then there's another cognitive agent that essentially does text processing. And there is another cognitive agent that is doing image processing. And this cognitive agent actually can correlate information between text processing and image processing and give you, a lot of different kinds of computing models. So essentially what this allows us to do is really integrate the symbolic computing as it exists and sub-symbolic computing as it exists, and essentially create the next layer of overlay, just like what the neocortex did, with the knowledge structures as the representing medium. So this provides essentially the knowledge structures, how you design them, using entities, relationships, and behaviors, and what is the schema of the knowledge structure, what are the operations in this and the knowledge structure. They're all defined by Mark Bergen and myself in a couple of papers, and we are using this now to essentially create the next generation structural machines. So we are going from Turing machines to structural machines, data structures to knowledge structures, and deep learning to deep reasoning. That's basically what, and these are some of the books, and there is a lot of papers that you can look up. Obviously, Mark has written enormous amount of literature on this, and I also have the TFPIS, theoretical foundations, www.tfpis.com. There is a large number of references. I have multiple blog posts there talking about in this detail and how to implement them. And I'm working with various people actually implementing different ways in order to infuse cognition and autopoiesis into existing